Let's start with the first one, the first in, first out algorithm. So this is simple as the name suggests. If all the frames are used, then you free the one that contains the page that was loaded more time ago. Okay, so here we have our reference string. Let's say we have 3 frames in total for the process, so we can only load up to 3 pages at a time for the process. Let's go through the example. It's simple. So we start here. Initially, all the frames are free. We didn't load anything yet. So we need page 7. Is it in one of the frames? No. Okay. Then we have one page fault and we put 7 here. Then we need 0. Do we have it? No. 2 page faults and we store 0 and then we go for 1, which results in the third page fault and we store 1. Now we need page 2. We are here. So we ask ourselves, is it there? No. Do we have a free frame? In this case, the answer is no. So in that case, we need to substitute the page that was loaded more time ago. This case would be 7. So we have 1 page fault and now 2 will be placed in the position where we had 7. Now we need 0. It's there, so it's fine, and so on and so forth. So if you do the entire, if you go through the entire reference string, you will see that at the end, we will have 15 page faults. Of course, you change the reference string, you will get a different number of page faults. Something that is interesting about this algorithm is that it can suffer for this, from this anomaly, the Belladis anomaly, which basically means that actually having more frames might result in having more page faults. The global tendency is the same. The more frames you have, the better. But for specific changes, going from n to n plus 1 frames might actually increase the number of page faults. Okay, and it's simple to implement because you basically use FIFO queue and then you always take the oldest you had in this first in, first out queue to select which is the victim frame if you need to swap out a page. And this is an example of this Belladis anomaly, and you can try it out by yourself. So you see that the tendency is it goes down, but actually there can be some spikes here. So when you go from 3 to 4 frames, actually you might experience more page faults than in this case, than when you had less frames, which with 3 would be 9 in this example. Now, one can ask, okay, we got 15 page faults with the FIFO algorithm. What is the optimal? What is the actual minimum number of page faults we can get? Well, it turns out that there is an optimal algorithm, and the idea is simple. If you have to replace a page, then you should replace the one that will not be used for the longest period of time, okay? And if you do this for our reference string, you will see that 9 is the lowest number of page faults you can get for this reference string if you have 3 frames that you can use for the process, okay? Now the problem is that you cannot really implement the optimal algorithm because in practice, you don't know which will be the page that will not be used for the longest period of time. Knowing that would basically mean reading the future for a generic process in a generic execution with many other processes. But still, you can use it at least as a means to understand how close you get with your algorithm to the optimal number. So you see that 15 versus 9 is actually not that good, okay? This is just the execution. You can try it out by yourself and you see that 9 is the total number of page faults we would get in this case. An algorithm that is used in practice that gets closer to the optimal one is the least recently used. So when you have to select a victim frame, instead of picking the one that will not be used for the longest period of time, you pick the one that has not been used for the longest period of time. The idea is that more or less this should be the same. If it is a lot of time I'm not using a certain frame, then most likely I will also not really use it a lot in the future. And this connects back to the concept of locality we already mentioned before. So this is what I just said, you replace the page that has not been used in the most amount of time, looking of course at the past, not at the future. So you can keep track of the time at which you access each page. And then when you have to select the victim frame, you pick the one that was not accessed for the longest time. So let's try to look here, for example. Here you need page 2, you need to select a victim frame. So which one do you pick here? Well, the one that you have used, that you have not been used, sorry, in the longest amount of time. In this case, it would be 7. So you pick 7. You can try this example, try please all these examples by yourself and check that your numbers match with these ones. And here you can see that you end up with 12 faults at the end of the day, which means in this case it's performing better than the first in, first out algorithm. Now, there are different ways in which you can implement this. Again, as always, different implementations means different trade-offs, different costs. You can go with a counter implementation. So basically, you keep the value of the clock, one for each page, and you update it whenever you access the page. When you have to select which is the victim frame, you take the one with the lowest value for the clock. That is the oldest one. Problem of this is pretty simple, but you need to search through all the table to keep track, to find what is the smallest clock value, because the table is not necessarily sorted on the clock values. Okay, so to update the table, it's O1 time, you just store the value of the clock, but to find the victim frame, it's ON, where N is the size of the page table. Otherwise, you can keep an additional data structure, in this case, a stack, okay? And whenever you reference a page, you go in the stack, you find where that page is, and you move it to the top. In this case, updating each entry takes a bit more because you have to search inside the stack and put it up, put the entry up at the top. But on the other end, when you have to find the victim frame, that becomes O1 time. It's fast because you know that what you have at the bottom of the stack is the page that you did not use for the longest amount of time. This is just an example. So if you are before year 7, this is the situation with the stack. You see that 2, it's on top because you just used it, and 4, it's at the bottom because it's the one that has not been used for the longest period of time. Now, if you want to access 7, you do that, you have it already, but then you pick it and you move it up to the top. And you see at the bottom, if you want to know which is the victim frame to choose when you need that, it's the one that is at the end, at the bottom of the stack. You can also write approximated version of this algorithm. One is to use simply a reference bit. When you load the page, the bit is 0, and when you reference the page, the bit is set to 1. Now, you only have 2 values, 0 and 1, so it's not really accurate. It's a very coarse-grained approximation, but if you have to select a victim frame, you can select one that has bit 0, because you know that at least the ones with bit 0 have been used before the ones that have bit 1. Alternatively, you can go for the second chance algorithm, okay? Here you have a description, but I think it's easier if I just show you how it works. So basically you have an extra bit for each entry, and you keep a circular queue of the pages, okay? So let's say that this is the page you are currently pointing at as the next victim. If you see 1, then you don't pick this as a victim, but you set it to 0 and you move to the next one. So you keep moving until you find one that has 0. As soon as you find 0, then that is the victim frame. So what is happening here is that if this is 1, it means that this page has been used. You put this to 0 before moving to the next page, which means you are giving a second chance to that page to be not selected as a victim frame, because you will keep looking at the other pages. If all the other pages have also the reference bit set to 1, then you will get back to this page. And if it is still 0, it means, well, then it's not really being used. So I will select it as a victim frame. If it went back to 1 because the process was actually using the page, then it will get again a second chance before being selected. This is why it's called the second chance page replacement algorithm, okay?